circuit tracer does indeed send a tone through an entire phase of an electrical system, extending through the circuit breaker and into the panel's bus. The mechanism behind this involves the circuit tracer acting as a sensitive radio receiver. It detects the electromagnetic field generated by the alternating current flowing through the wire. The electromagnetic field strength is directly proportional to the current's magnitude. A stronger current produces a more potent field, making the signal easier for the circuit tracer to detect. When the circuit tracer is connected to a wire, it introduces a high-frequency signal into that wire. This signal propagates through the wire and enters the electrical panel. If the circuit is complete, the signal will pass through the circuit breaker and return to the circuit tracer, which then registers the signal and produces an audible tone. However, a significant issue arises because the signal is not confined to the intended circuit. It can also propagate through other wires that share the same phase as the wire being traced. Consequently, tracing efforts may inadvertently encompass an entire phase of the electrical system, even when the objective is to isolate a single circuit. To mitigate this problem, there are several strategies. Firstly, connect the circuit tracer to the wire as closely as possible to the circuit breaker. This minimizes the length of wire available for the signal to bleed into other nearby conductors. Secondly, utilize a circuit tracer characterized by a high signal-to-noise ratio. This feature reduces the likelihood of interference from other wires, allowing for more precise tracing. Finally, recognize that pinpointing a specific circuit may necessitate tracing multiple circuits, particularly in older buildings with potentially disorganized wiring systems. Understanding circuit tracers requires knowledge of fundamental electrical principles. Alternating current, or AC, is the type of electrical current primarily used in residential and commercial buildings. Unlike direct current, or DC, where the flow of electricity is unidirectional, AC changes direction periodically. This change in direction is measured in Hertz, or Ht, which represents the number of cycles per second. In the United States, the standard frequency for AC power is 60 Hz. This means that the current changes direction 60 times per second. The flow of AC creates an electromagnetic field around the conductor. The characteristics of this field, like its strength and range, are directly related to the current's magnitude in the conductor's geometry. The circuit tracer takes advantage of this electromagnetic field. It emits a signal that interacts with the field and allows the user to follow the path of the current. A typical circuit tracer comprises two main components: a transmitter and a receiver. The transmitter injects a specific signal into the circuit under investigation. This signal is a low-power, high-frequency AC signal. The receiver is a handheld device that detects the signal emitted by the transmitter. It uses a sensor, typically an inductor pickup, to detect the electromagnetic field generated by the signal. The receiver then amplifies the signal and converts it into an audible tone or a visual indication on a screen. The closer the receiver is to the wire carrying the signal, the stronger the signal and the louder the tone. By following the tone, the user can trace the path of the circuit. Several factors can affect the accuracy and effectiveness of circuit tracing. Wire gauge is a significant factor. Thicker wires, with their lower resistance, allow the signal to travel further and more clearly. The type of insulation around a wire also plays a role. Some insulation materials can dampen the signal, making it harder to detect. The presence of other electrical equipment nearby can also interfere with the signal. Motors, transformers, and other devices can generate electromagnetic fields that can mask the signal from the circuit tracer. In addition, the way the building is wired can also affect the tracing process. In older buildings, the wiring may not be well organized or properly labeled. This can make it difficult to identify the correct circuit. Furthermore, shared neutrals and multi-wire branch circuits can create complex paths for the signal to follow, leading to confusion. In these cases, it is important to take extra care to ensure that the correct circuit is being traced. In addition to the potential for tracing an entire phase, there are other limitations to be aware of. Ground faults can create false readings. A ground fault occurs when a live wire comes into contact with a grounded surface. This can cause the signal to travel through the grounding system, making it difficult to pinpoint the exact location of the fault. Open circuits can also be difficult to trace. An open circuit occurs when there is a break in the wire, preventing the signal from flowing through the circuit. In this case, the circuit tracer will only be able to trace the circuit up to the point of the break. When using a circuit tracer, it is important to follow all safety precautions. Always disconnect the power to the circuit before connecting the transmitter. Wear appropriate personal protective equipment, such as gloves and safety glasses. Be aware of the potential hazards of working with electricity and take steps to avoid them. The NEC, or National Electrical Code, provides guidelines for safe electrical installations. It is important to be familiar with the NEC requirements for circuit tracing. For example, the NEC requires that all electrical panels be properly labeled. This can make it easier to identify the correct circuit. The NEC also requires that all wiring be installed in a neat and workmanlike manner. This can help to prevent problems with circuit tracing. In addition to the NEC, there are other resources available to help with circuit tracing. Electrical contractors associations and trade schools offer training courses on circuit tracing techniques. There are also numerous online resources, such as articles, videos, and forums, that can provide helpful information. To effectively use a circuit tracer, consider several techniques. Firstly, isolate the circuit. Turn off the circuit breaker for the circuit you want to trace. This will prevent the signal from traveling through other circuits. Secondly, connect the transmitter. Connect the transmitter to the wire you want to trace. Make sure the connection is secure and that the transmitter is properly grounded. Thirdly, adjust the sensitivity. Adjust the sensitivity of the receiver so that it is sensitive enough to detect the signal, but not so sensitive that it picks up interference from other sources. Fourthly, follow the signal. Use the receiver to follow the signal along the path of the circuit. Move the receiver slowly and deliberately, paying attention to the strength of the signal. Fifthly, verify the circuit. Once you have traced the circuit, verify that it is the correct circuit by checking the voltage and current. In summary, circuit tracers are valuable tools for electrical troubleshooting, but understanding their limitations and employing proper techniques are crucial for accurate and safe usage. By understanding the principles behind circuit tracing, recognizing potential sources of error, and adhering to safety guidelines, electrical professionals can effectively utilize these tools to diagnose and resolve electrical issues. The proper use of a circuit tracer will save time and effort when compared to other methods. Using a multimeter can be time-consuming, as each wire has to be tested individually. Visually inspecting the wiring can be helpful, but can often be difficult to follow wires behind walls and in conduit. A circuit tracer is a non-destructive method, unlike cutting into wires to test them. Some advanced circuit tracers have features that can further improve their accuracy and effectiveness. Some models have adjustable frequency settings. This allows the user to select a frequency that is less likely to be interfered with by other electrical equipment. Some models also have filters that can block out unwanted noise. Other advanced circuit tracers use signal processing techniques to improve the signal-to-noise ratio. These techniques can help to reduce the amount of interference from other wires and make it easier to trace the circuit. Many circuit tracers include features to identify breakers. A breaker finder is a type of circuit tracer that is specifically designed to identify the circuit breaker that corresponds to a particular outlet or fixture. These devices typically consist of a transmitter that is plugged into the outlet or fixture and a receiver that is used to scan the circuit breakers in the electrical panel. When the receiver detects the signal from the transmitter, it indicates which breaker is connected to the outlet or fixture. Some breaker finders use a simple audible tone to indicate the correct breaker, while others use a visual display or a combination of both. To effectively use a breaker finder, it is important to follow the manufacturer's instructions and to take precautions to avoid electrical shock. Also, remember that even with a breaker finder, there is always the chance of tracing errors. It is always best to double-check the results with a multimeter before working on any electrical circuit. When selecting a circuit tracer, there are several factors to consider. The size and weight of the unit are important, especially if you will be using it in tight spaces. The battery life is also a factor, as you don't want to be constantly replacing the batteries. The price is always a consideration, but it is important to remember that you get what you pay for. A cheaper unit may not be as accurate or reliable as a more expensive unit. It is also important to consider the features that are included with the unit. Some units come with additional features, such as a built-in multimeter or a flashlight. The NEC also covers the use of circuit tracers in specific applications. For example, the NEC requires that circuit tracers be used when working on energized circuits. This is to help prevent electrical shock. The NEC also requires that circuit tracers be used when working on circuits that are difficult to access. This is to help ensure that the work is done safely and efficiently. The use of a circuit tracer is not a substitute for proper electrical safety procedures. Always disconnect the power to the circuit before working on it. Wear appropriate personal protective equipment, such as gloves and safety glasses. Be aware of the potential hazards of working with electricity and take steps to avoid them. Firstly, understand the limitations of circuit tracers, as they can send signals through an entire phase. Secondly, minimize errors by connecting close to the breaker and using a high signal-to-noise ratio device. Thirdly, remember older wiring may need multiple circuit tracers.